Hello YouTube RJ. Today we're going to do a video where we begin our transition into creating a HF ham radio. Now this will be videos that are intermixed with other content as we go along, but this is going to be kind of a series. So I wanted to get started with a video before we dive into creating the different modules of electronics to build the radio from. I wanted to start out with a theory. I want to make sure that we understand what we're doing as we go, and hopefully maybe you learned something. So this video is the prelude to building and testing our broadcast filter. Now, a broadcast filter's job is to make sure those frequencies lower than what we want to deal with gets filtered from our receiver prior to even entering the receiver, right off the antenna basically. We want to take and strip away things from the lower end, and the reason is below the ham bands is the broadcast band. And the broadcast band has some very large transmitters. You can have some really high wattage transmitters out there, and they can just literally overload the front end of your ham receiver. So you need a way to just get rid of them right off the bat. We don't want to do anything with them. They're going to be picked up by our antenna, but from that point, we want to see if we can diminish those signals as low as possible. So that's where our broadcast filter is going to come in. What we're going to do in this video is we're going to look at designing a filter, how a filter works. We're going to talk about LC circuits, inductor capacitive circuits, and how we can use them to filter signals we don't want. Now there's multiple types of filters. This particular filter is going to be what's called a high pass filter. And the reason is because the higher frequencies will pass right through the filter. The lower frequencies are the ones that will prevent filter. Hopefully you'll learn something from this. Hopefully it'll be interesting. I'm going to try to not get too technical with the math and all of that. I'm going to keep it simple. I'm going to explain it from more of a layman's terms of what's going on, and that'll give you a good footing. If you're not that familiar, maybe you know how it works and you're just a little iffy on it, or maybe you know more than I do about it. That's probably quite possible. But we're going to take on this task of designing our own filter, and like I said, the next video that'll come out will be us building and testing and seeing how well did we do compared to what we designed and what we expected and our expectations of it. How did we come out with the build? Let's get right into it. Okay, so if we're going to design filters, we're going to need some software tools to make our life easier. Now there's a couple ways you can do it. You can definitely do this in LT Spice. I'm going to show that in a moment. But there's also a software called ELSIE, E-L-S-I-E, free download. The Pro version, you have to buy a key for 95 bucks. I'm not using the Pro, I'm just using the student free version. So you download it and install it in your computer. We'll start up ELSIE here. With this software, you're going to spend 30 minutes, 45 minutes, an hour, maybe learning your way around in here. There's a good manual that'll help you. That's going to help you design the filter, but you got to have a starting point. We have to have an idea where we need to start so we can tweak and play with our filter. So what I like to do is I like to go to one of these LC filter calculators. And this one here is on electronicbase.net. You can see the link there. I'll put the link down in the description of this video. What I like to do is I like to go in and I like to take a look at a reasonable size inductor, something that I'm going to be able to get. In this case, I'm using a 2.2 microhenry. I'm going to ask it to tell me what capacitor to use with this. Okay, so I'm going to say, okay, calculate the capacitor. Here's the inductor I'm going to use, and I need a cutoff. We're going to be using 3.5 megahertz and up, so we want to be well below that. So let's say 2.4 megahertz. We could be a little lower than that without a problem, but let's say 2.4 megahertz, and let's calculate that. And you see it comes up with a 2 nanofarad, or in other words, 2000 picofarad, depending on how you want to look at it, capacitor. So now that we've got that out of the way, let's get into LC. Now I already kind of started this design, and so I'm going to just load it so that we can get going quicker. Here it is. You're looking at a signal generator here. This is going to put out a varying frequency. This is going to terminate it for 50 ohm impedance. This is your load on the other end, which would be a 50 ohm amplifier, whatever circuitry you're going into. And then what we've done is we've added a 2000 picofarad capacitor in series and a 2.2 microhenry inductor in parallel to ground. So what this is going to do is this is going to filter out things that are below certain frequency. And how this works, and I know this is a very simplistic way to describe it, and I don't want to get in a big argument on it, but basically think of it as this. A capacitor allows signals to go through at higher frequency. The higher the frequency, the easier a signal can get through a capacitor. The lower the frequency, the harder it is to get it. When we build electronic circuits and radios, we're often needing to capacitive couple circuits together because we'll have a DC bias on this side that we do not want to get to this side of the circuit. So we'll throw a capacitor in there. What that does is that DC signal is as low a frequency as you could get, right? It's 0 hertz. So a capacitor does a very effective job of blocking that and not allowing that DC signal through. Although our AC, small signals from our oscillators and such go right through, so it doesn't cause a problem. So this is going to let higher frequencies through, lower frequencies it's going to try to block. On the other end of that, you've got an inductor. So here is our LC circuit. So our inductor, an inductor at low frequency, say DC, 0 hertz, right? Just looks like a coil of wire. It's just a very low resistance. So low frequencies would easily go to ground here. And that would ground out the signal. But as you increase the frequency, this more and more looks like a higher and higher resistance resistor, basically. The impedance of this to an AC signal increases as the frequency goes up. So as you send a signal through here, your low frequencies tend to get blocked through here, right? But with an inductor, it's the opposite. The frequency goes up, this becomes a higher and higher resistor, basically. The impedance increases and increases. So at low frequency, this thing looks like a direct short almost. So any low frequency signals get shunted straight to ground and are done away with. As the frequency goes up, this becomes a higher and higher valued resistor, so less and less of the signal can go through here, so the signal reaching here goes up and up and up. What happens is lower frequencies come through and get shunted to ground, higher frequencies go on their merry way. Now, it's not perfect. It doesn't completely block everything, and we're going to show how that works. But we've set up for what our calculator, and it said, about 2.4 would be the resonance. So let's plot this circuit out. Well, if we plot this circuit out, here's 3, so 2.4, your cutoff it will be minus 3 dB. So you're going to take a measurement at minus 3 dB, and you're going to end up about 2.4 or so, somewhere in here. So I would say that is fairly accurate. Now, looking at this as far as being a high-pass filter, it's not a very good one for us. And the reason for that is, well, it has very low insertion loss. As you get up in the frequencies, you're not reducing the signal very much. 10 dB is not going to cut it for us. We need a better filter. This filter is just not adequate. That's why it's not as simple as just a single inductor and capacitor. That just doesn't typically work. And why is that? Well, because this has some resistance, even at low frequency. These devices are not perfect. They have parasitic resistance, if you will. So what happens is it doesn't let all the signals shunt. The lower frequencies, all of it doesn't get shunted. So how could we improve this? Well, what if we did the same thing again, added another section of this, okay? And this is where you hear filters 3-pole, 5-pole, 7-pole. This is what they're talking about. How many sections of an LC are you using to actually filter? If we added another one, if this one took a certain amount out, the next one should take some additional out. So let's see what happens. What we do is real easy to work with. Click on the section and insert a part prior. Now we've got to tell it what part we want. We want a series capacitor. We have to put the value in. So let's do another 2000 picofarad. Hit the right key, be great. Okay, we're going to click here again and add another part, and this time we're going to put a parallel inductor, and it's going to be 2.2 microhenry. So we've just duplicated this section and added a second section. Now, is that going to gain us anything? Well, let's look. Yeah, it did. We're getting over negative 20 dB rejection. We've added a little bit of droop in here, but that's not going to be a problem. In fact, you're going to see that gets better anyway. We're looking at making sure that at 3.5 right in here, we want to have the least amount of loss we can have at that point, and then below that start dropping off. And somewhere under 2 megs at this point is where it really starts to drop off. So what happens if we make this a 3-pole? Let's go in and add another section. We need to add another capacitor. Okay, we're going to add another section. We're going to add another inductor. Okay, now what do we look like? We're doing even better. Still got a pretty good droop here, but here's 2 megs here. Here is 3.5 here. So we have some insertion loss that gets better as we go up, but it's not that bad. It's not that high. That's something I think we can work with. Let's put a marker in at 3.5 and see. Okay, 3.5. We're under a dB loss. That's this here. Turn that marker off. Get that out of there. That didn't help me. This is a much better way of doing it. Here's 3.5, and we're under, if you look down where it says trans, minus 0.98092. We're less than 1 dB loss. So that's really good. That's really good. So we do have a little bit more loss here, but we're well below the frequency we're using, so we won't losses down here. Then the cutoff is going to be right about, let's try to get as close to 3 dB loss, around 1.4 meg according to ELSI. Okay, so the question becomes, can we improve this? Well, sure we can. Filters are one of those things that you tweak and you play with and you carry on, and one thing we could do is, why don't we add another pole? So what if we go in here and insert another capacitor? Okay, and we want to add another inductor. We want to close out with a capacitor. That's typically what you do. So let's see what that does. Well, that improved us even more. Here's our 3.5 right here. We've got a little more loss, but we don't have, it's a little flatter in here. Okay, so that looks a lot better. But if you notice, we're using all the same capacitors and all the same inductors. And I like all the same inductors, but I find that sometimes you get your filters to work a little better if you don't use the exact same capacitor all the way across. So let's do a little editing. Let's say, what happens if we change these at 1,000 picofarad? What happens? Wow, look at that. And I won't get into why that is. That's one of those things that really gets into the math too heavy, but your filters won't always have the same capacitors. They sometimes won't have the same inductor. But what you will always find is they typically are a mirror. If you look at this, 1,000, 1,000, 2,000, and 2,000, you always want to mirror. You always want to kind of mirror it. That's a typical design of a filter. You'll see this over and over again. So playing around with these values, I've come up with a filter that I look at the plot and I say, I really like that. 3.5 is right here. Let's get our measurement. Wow, this thing thinks we're going to have like almost no insertion loss all the way up through. You got a little dip here, but when you get to about right at a really close to 2 megahertz, you start dropping dramatically. And if we get to 3, if you can see on the screen there where it says trans, minus 3 dB is 1.822 megahertz. So that would be perfect. This filter would be a perfect broadcast filter for us. And so this is what we're going to go with. And so this is our design. We're going to build a filter to match this, and this is how I came up with those values. Now, one thing I did want to show you is I wanted to pull over LT Spice. Done the same thing in LT Spice. And the reason I want to show this is we've built up the same filter here. The only difference, you don't see a resistor here. It's because in LT Spice you can actually set the resistance. See here, the resistance, serial resistance is 50, so that replaces that resistor I had here before. We still have our load here. We still have our 2,000 and 1,000 picofarad capacitors. Now, if I do an analysis of this, let's run it. Let's see what it thinks and how it compares to LC. Okay, and we want to take a reading here. Okay, so here we are. It looks like the cutoff probably is in about the same place. Let's look at our screen here, and let's call it minus 7 dB, so it'd be minus 10 dB to get to 3. So minus 10 dB is right about there. So that's 1.845 megahertz. So they agree somewhat, with a couple of exceptions. One is, notice how much insertion loss that LT Spice claims we're going to have. It's talking 6 and 7. You know, by the time we get to 3.5, it's 6.8 dB, minus 6.8 dB. So it believes a lot of loss, and it believes we should get down to, let's get down here. It believes we'll get down to minus 58, almost minus 59 dB down at 1 megahertz. So that's LT Spice. When we look here, LT shows us getting a little less, but a lot less insertion. And if you add the insertion loss to this here, you come out about the same. LT Spice has always had a habit of showing a lot of insertion loss for some reason on these circuits, and that's just something I've noticed. LC, in my opinion, comes out a lot closer. So the interesting thing is, we're going to take a look at this when we build our circuit and we test it in our next video. I'll bring up the LT Spice and show you how it compared to the actual circuit, and I think you'll agree the circuit will come out much closer to this than it will to the LT Spice. I hope you've learned something. Hope this was informational. Feel free to subscribe to the channel if you're finding this content interesting. Give me some feedback. Tell me what you'd like to see. That's how the channel gets better, is with your input. So thanks again. Hope to see you on the next video.